Hey everyone. Yes, so I'm Lindsay. I guess I am a WIMP hunter. I build detectors, right? WIMP detectors are interesting. Dark matter is like a weird sort of particle physics where you have to build these really complicated, precise experiments deep underground. There's going to be some details in the talks that Lockie and Guy will give on the experiments that I work on, but I kind of want to take a step back with my talk and try and justify why we do these kind of crazy things. Why do we build this lab a kilometre underground? Why do we look for a WIMP in particular? What makes me think that it's that and not something else that we haven't imagined, right? Like, why isn't dark matter jelly beans? Like that. So I mean, how do we actually come up with the knowledge, right? How do we make this best guess that we have that dark matter is WIMPs? And I mean, we were going to get Ben here. Ben couldn't make it because his flight was cancelled because of the airport thing today. And dark matter could also be axions, right? So I mean, WIMP detectors are weird. We look for these particles deep underground. Axion detectors are arguably weirder. They try and tune into. Thank you. They try and tune into dark matter with essentially a radio, right? So they change the channel on the radio and they look for a signal from the dark matter. Or they shine a light at a wall and look on the other side to see if the light has come through. They do all sorts of crazy stuff like that. So I mean, it's a shame that Ben couldn't be here. But yeah, I kind of want to justify to you, right, the tax-paying public, why we are spending your money on this. There's lots of real things to spend it on. Yes, dark matter is probably real, but we think we might find it, and so yeah, I kind of feel beholden on explaining this. It's a bit embarrassing, really. The key thing that I need you to understand is that it's actually a miracle, right? So there's this thing called the WIMP miracle that we've noticed. It's actually more like a WIMP coincidence, but I'm an atheist, so it's more or less the same thing for me. And to explain the WIMP miracle, I need to talk about the Big Bang, right? So have people here, I assume, have talked about the Big Bang. We've just talked about the Big Bang. So if you look at the history of the universe, what has happened over the history of the universe is things have expanded and cooled down, right? And so if you run the clock backwards, right, you go back to this hot, dense state that's in the song, like at the very early times in the universe, at the time of the Big Bang, there's a lot of energy, right? In this hot, dense state. A lot of energy equals mc squared, or as Phil points out, it's ish. We have, and what equals mc squared means actually, right? Like everyone knows this equation, right? Everyone knows E equals mc squared. What it actually means in practice is that you can turn energy into mass and vice versa, right? So very early universe, you can generate a lot of particles. You can generate mass. So the fundamental particles are all there. All the ones that can couple to the early universe energy. And so if dark matter is a particle, it's also hanging out, right? And the way I want to kind of explain this to you is kind of like it's a party, right? Because they're particles. Thank you. That's getting my dad jokes out. Pulled that one out of the database. Keep going. One more? I mean, I think I'm the only dad that's speaking, so that's good, right? Because it's not a faux pas. It's one for Cedric. Okay, so yeah, I'll stop now. So early universe, there's all these particles. I don't even remember what I was talking about. The WIMP miracle, right? So the question is, when do the particles leave the party, right? Because what happens is eventually, the particles are sort of like, hanging out at this party, and eventually they'll leave. And this is actually what happens, right? And so, what are the properties of a particle that will cause it to leave the party in the early universe? What are the properties that will cause it to, exit and fly off and stop interacting so much with the other particles? So there's two things, right? One is the mass. So the mass, you can kind of understand from E equals mc squared as the universe cools down, right? As the party dies down. The ones that leave first are the heavy particles, right? They like it hot, right? They like the party, when it's really pumping, and when it's calmed down, they kind of leave because the energy has dropped below their level, right? So you can't produce that mass anymore, and so they fly off, right? They all other things being equal, the heavier particles will leave the party early. And then the other thing is the interactions, right? So how much do the particles like to interact? And so there's some particles like to really interact, so they like to get out there, hang out with the other particles, and other ones are sort of socially awkward, and they prefer not to hang out with the other particles at the party. And so they will be, the first ones to leave, right? And so the intuition that I want you to have is that, at the time of the Big Bang, the particles that will leave the party first will be the heavy, awkward particles. What's that?
The engineers.
Yes. Yes. Okay. I mean, my experience of engineers is that they can party, right? They got boring jobs by and large, so I don't know. Judgy. So you got to make up. But no. There's the heavy particles that don't like to hang out with the other particles that leave first, right? And the lighter, more social particles will stick around. So then they'll take off. And so what we can do, right, is that if once those particles leave the party, if they're stable, they'll essentially fly off into the universe and they'll keep existing, and we can measure them today. So this is what we've done with dark matter. This is how we know that of the universe, 25% of the universe, the mass energy of the universe is dark matter, and so the thing that you can do is you can actually write down, a relation between the mass of the particles, the interaction strength of a particle, and the amount that's left today, right? And so we can do this for dark matter, and so we've got two things that we don't know. And we've got one thing that we know, right? We know how much dark matter there is today. And if you look at that, you can say, well, okay, we've got two things. I mean, there's not a lot we can say, right? Like there's the mass could be anything, and the interaction strength could be anything. We don't know exactly, how heavy it is or what its interaction strength is. But the Witt miracle is this, right? If you give the dark matter the same interaction strength as one of the four fundamental forces, so the weak interactions, it's the Witt miracles, a weakly interacting massive particle. If you give it the same interaction strength as the other, as the weak particles, then the mass is completely unconstrained. And so the mass of the standard model particles has a big range, right? So we know a lot of particles that exist. There's neutrinos. Neutrinos are really light, and then you kind of get heavier. So a proton is about 100 million times heavier than a neutrino. There's the weak interaction mediators, the W and the Z. So they're about 100 times heavier than a proton. And then there's it's a range of billions and billions, right, across the mass of the particles. And we don't know what mass the dark matter ought to have. It could be lighter than the lightest particle. It could be a trillion times heavier than the heaviest particle. So the Witt miracle is that when you give dark matter, and you say, well, we know how much there is now if we had the interaction strength of the weak interactions, the mass that you come up with is exactly the same mass as the mass of the weak interaction mediating particles, right? So the W and the Z. So it could have taken anything. Whoa, yes. Could have taken anything, and it takes that instead. So it's a hint, right? So it's not a miracle, right? It's a coincidence. It's a weird coincidence. and this is literally the basis of you know, $100 million worth of experiments or so, right? Like, we've spent a lot of money looking for WIMP dark matter, and so it's a very exciting thing. I mean, the reason that these experiments are so exciting are because and so expensive actually is because the weak interactions are really hard to measure. Right, so the weak interactions, just to give some sort of sense of the scale, you can make a beam of neutrinos, right? So neutrinos interact weakly and nothing else, and you know, you can try and put some stuff in the way to try and stop that beam, right? So let's say we put some lead in the way of a beam of neutrinos, and you want to stop, you know, maybe not all of it, but half the beam. Does anyone want to hazard a guess how much lead you'd need to kind of stop a beam of neutrinos? A meter? That's a good guess. 1 kilometre? Keep going. A light year. Thank you, Aramis. My daughter. I've taught her well. So yeah, you need about a light year, which is, you know, if you don't know what a light year is, it's a bloody long way, right? Like, and so, you know, this kind of illustrates the scale, right? We build a detector. Saber's like a pretty big experiment that we're building at the moment. And what we expect when we do these measurements with Saber, we expect maybe a few counts per day, right? A few events per day of dark matter interacting in the detector, which is not a lot when you consider the backgrounds. So the backgrounds that we'll see are sort of, well, higher. If we were to do it on the surface of the Earth, it'd be really high, right? So the cosmic rays that Phil mentioned and that Susanna mentioned, you know, every square meter of Earth that we have here gets hit by about 1 million cosmic rays per day. Your body, you would make a terrible dark matter detector because you're far too radioactive, right? Every kilogram of your body contains about 10 million radioactive decays per day. So, you know, like you won't see the few dark matter events per day that you'd expect. And so we need to build these really crazy, really precise experiments. So hopefully I've justified why we exist as taxpayers. Please write to your local MP and thank them for their support. And thanks for your time.